Good morning, folks. This is lecture 9 on February 2nd, 2023. And it is a continuation of what we started today, or actually on Tuesday. And it deals with the force vibration under harmonic loading. The good news is that the first maybe 5 or 6 slides is a review process, review of what we did earlier. I went through it very quickly, so let's spend a little bit more time here and go through them one by one. So there's the agenda. We started this forced harmonic vibration on Tuesday, and we also talked about the steady state response, but this is going to be a review and some examples that we're going to do. All right, so we have a damped vibrating system, so mass spring damper system, and it's subjected to a load F of T. That's why we say it's a force vibration, okay? But the load F of T is of a very special type. It's of if it's a cosine type, so it changes in a sinusoidal manner, cosinusoidal manner as a function of time. So it's effectively is F naught cosine of omega T. This is the mother of all equation. Instead of being 0, which is the first 3 weeks of the course, it's forced F naught cosine omega T. Okay? Now, the first thing I'm going to do, I'm going to divide through by m. That's what we did. And when you divide by m, you get k over m here, which is incidentally omega n squared. And c over m, if you fool around with it, you see that it's actually this thing. Remember, c over m, if you write c as uh, uh, zeta times c critical, and C critical is 2m omega n. Notice that you divided by m, so the m disappears and you get 2 zeta omega n. And on this side, you have F naught over m, big F naught over m. So Inman calls that thing little F naught, okay? There we are. Little f naught is big F naught over m, and obviously omega n is root of km, k over m, and zeta is c over c critical, and c critical is either 2 square root of mk or 2m omega n. Okay, so we already know all of these. Now, uh, the solution to this equation, because there is damping involved, is going to, the particular solution to this equation is going to be big X that we have to find, cosine of omega t. Now notice that this omega is exactly the frequency, the driving frequency that appeared in the right-hand side of your forced harmonic response, okay? This is the same frequency as the applied load, this omega. That's very important. This is not omega n. It's the same frequency that we applied to the load. And this theta, if there is no damping, this theta is going to be 0. And that's called, that's what we did on Tuesday at the beginning, no damping. If there's no damping, theta is equal to 0. The particular solution was big X omega t. But when there is damping, you must include theta, and you have to find big X and theta, okay? Now, there's another way of writing this, and that is expanding cosine of omega t minus theta. In other words, cosine of the difference of two uh, uh, angles. You can expand that using the trig identity. You're going to have, if you expand this thing, you're going to get cosine omega t plus cosine theta and plus sine omega t sine theta. And if that is the case, then that cosine of theta times x, you can call it as, etc. So this can also be written as the product of an unknown, an unknown times cosine of omega t plus another unknown times sine of omega t. And this as and bs come from when you expand cosine of the difference of two angles and clean it up. That's what you're going to get. Okay. All right. So what we did next, we took that xp and the derivative of it and the second derivative and stuck it into the differential equation and brought all the cosine omega t's and sine of omega t's, factored them out, and put them on the left-hand side. So we have some algebra. Uh, Stuff involving cosine of omega t is this bracket. Stuff involving sine of omega t is this bracket. And if this is to be 0, the first bracket must be 0, and the second bracket must be 0, and that will give you two equations, two unknowns. What are the two unknowns? AS and BS. So, you know, from your elementary high school algebra or first year, algebra, mechanics, first year linear algebra, you just solve this thing very straightforward and you get this. Now that you got that, you can put these things back into the expression. Can I back up for a second? You can put these things back into this expression. This expression, you found AS, you found BS. So go and clean it up, put it in there, clean it up, and you're going to get the particular solution using the trick in trigonometry that you have the cosine of some an angle times a constant plus sine of the same angle times a constant. You can put it together into an amplitude and a phase. Please go ahead, look at these things that we did 2 weeks ago. If there are any issues, come and see me, okay? You gotta get a hang of this. Okay. All right, good. So notice that, by the way, let me go back here. So this xp of t, the particular solution, is an amplitude, big X, cosine of same driving frequency omega t minus a phase, okay? And notice that if zeta is 0, no damping, it reduces to what we did at the beginning of Tuesday's lecture, undamped force vibration, okay? But if you have damping, immediately you're going to get that phase shift, okay? Now notice that the initial condition may be specified, and if that is the case, you have the total solution is what we just got. This is called particular solution or the steady state response, okay? And then there's an initial or transient, there's a transient or dying solution, or what your math prof might have called the homogeneous solution, okay? Notice that as time goes on, this e to the minus something t goes to 0. As time goes on, this is going to go to 0, and you're dealing with the steady state response, which is right here, okay? Which was our xp, by the way. Now, notice that this stuff, somebody has done the hard work for us. Inman has done the hard work. And if you have initial condition x naught and v naught, and you want to know what big A and phi is, then big X and theta is, the big X and theta already we know. It's from the previous slide. We already know big X and theta, no problem. But if you want to know what big A and phi is, Inman has done the hard work for us, and he come up with phi equal to this and A equal to that in terms of the initial condition. I give you these, you plug it in here, you find phi and you find A, okay? And obviously theta and x are there. Now notice that this theta and x appears in phi and A. In other words, you cannot do this thing independently of the steady state solution. And I'll do an example, because we had formulas for big A and phi from the first 2 weeks of the classes, but there we didn't have this guy. The A and the phi from there is different from the A and the phi for today. Okay, just be careful, because we had an expression for A and a phi from 2-3 weeks ago, but that was uh, free vibration. Now we have forced vibration. A and phi are more complicated, and it involved big X and theta. Okay, there's a big difference. Okay, so in the book, if you're following the book, this is coming from window 2.3, but anyway, it's right here. Now, notice that this is one way of finding the A and phi. It's right here. Or if you decide to write it as e to the minus times sine of this plus e to the minus times the cosine of that, okay, there is an alternative way. Remember, when you look at this condition, when you look at this solution, this dying solution, there's two ways to write it. One is just like I did. The other one is to say C1, a constant times exponential times sine of that, plus another constant times exponential times the cosine of omega d. Okay, that's, see, remember, this can be written like that, but it can also be written as a constant e to the minus times sine plus another constant e to the minus times cosine of omega dt. So here in the next slide, that's the approach that is going to be taken right there. So you can write it as a1 times this constant exponential times cosine plus another constant times exponential times sine. These two, if you combine it, you get that previous expression in terms of amplitude and phase. But Inman has done the hard work for us and come up with these things. So he found out what A1 is. This horrible thing is A1. Found out what A2 is. This horrible 2 is A2. And notice that in it, I have things involving X naught and V naught. I have it in there. Okay. As a matter of fact, this whole thing, where is that? Let me see. I'll show you in just a second. This thing is A1 times cosine. You can see that. This whole thing, terrible, is A2 times sine. And of course, that stays the way it is. Okay, so this thing, you can write it like that, or you can write it like so. If you go back 3 slides, 4 slides ago, you see that it's written like this or it's written like that, either way. So this is the dying solution. This is the steady state solution, which will not die. Now, the effect of damping is there in that steady state solution. See that side? See that side? So, and see that side? So the damping does not go away in the steady state solution. We know that it's going to be there, and it's right there and right there. Okay? Now, let's move on. Here's an example. So we have we want to find that the constant of integration a and phi, and remember a and phi, there was an expression for it when we did undamped, free vibration, and today the a and phi, which involves forced vibration. I want to show you that if you make a mistake and use the expressions that we learned 3 weeks ago and find the a and phi, which is for a different problem, you're going to get completely different answer. Okay, so here's the situation. We know omega n, we know the driving frequency, we know the damping ratio, and the amplitude of the vibration, amplitude of the load, F naught, and the mass. And the initial conditions are initial displacement of 0.05 meters, which is 5 centimeter, and release from rest. So I want to find A and phi based on the stuff that we learned today, and also get A and phi based on the stuff that we got 3 weeks ago, and show you that they're completely different. And in fact, you should use the stuff that you learned today if you have a problem like that. These are all given. right? Everything is given, says in the statement of the problem. So first thing that we're going to need is we're going to need the damping frequency, omega n square root of 1 minus xi squared. You just plug it in. Your omega n is 10, and xi is zero point 0.01. Just work it out. And remember, there's a little f naught, so you find the ratio of these two, you get 10. So this is the steady state response. Steady state response. That does not die out. This is the second term of the general solution. Big X like that, and theta like so. Plug in these values, you're going to get 0.133 meters and 0.013 radian. This is not A and phi. This is for the steady state response. There is big X and theta. You will need this theta and big X in order to find A and phi. Let's go to the next line. So the general solution is like so. This is the steady state. This is the dying solution. To find A and phi, you are going to need this X and theta. Okay, let's plug in actually what we already know. Notice that psi omega n is 0.1 and omega d we just got. So I just plug in the stuff that we already know. Still, we do not know A and phi. The purpose of this problem is to find A and phi based on what we learned today and compare it based on what was presented to us 2-3 weeks ago, which is completely wrong for the present problem because our present problem is forced, is a force vibration. But first, let's do the what we learned today is right here. We know x, we know theta, everything else in this expression we know. We get 1.55 for the phase angle of that first expression, and we calculate big A, plug it in, we get this. Now let's go back to the stuff that we learned 2 weeks ago, 3 weeks ago for free vibration. Okay, right there. The expression looked like this. Free vibration. You plug it in, you get 1561. Look, this is 155. Not very far. Okay? Not close. I mean, not very far. They're almost the same. But when you look at A from 2-3 weeks ago, you get 0.05. That thing is completely different. This was negative 0.083 and this is 0.05. So there is a big difference between these amplitudes. And in fact, this is wrong for the present problem. If you have a force problem, force vibration under harmonic loading, you cannot use these things from 3 weeks ago, which was for free response. You have to use these expressions. And that's what this is saying. Okay? So the amplitude of the transient is greatly increased. See, the value of the constants of integration are greatly affected by the forcing term. Forcing term must be included, and you can see that it affects the values, okay? In particular, the amplitude of the transient is greatly increased, okay? This is the amplitude right there, greatly increased. It goes from 0.05 to 0.08. That's a big jump, okay? And the phase is reduced. Notice that 1561 goes to 155. If you use force response, amplitude is increased and phase is reduced. Anyway, this is wrong. Can't use this. Wrong for the present problem. This was all okay for free response. Okay. Now the question is, because the first term is dying out, should we ever worry about it? And the answer is, well, maybe. The decision to ignore the transient part of the solution or not should also be based on the application. So it's application dependent. For example, in the case of earthquake analysis, that transient is very important because after all the fatalities and things like that are during the, or destruction, of fatalities, hopefully, destruction or during the transient response. The first few seconds is transient, it goes by, but that's where the most of the damage is done. Okay, so I mean, you really, for design purposes, we usually ignore that, at least design of mechanical component. We usually ignore that, but we also have to check and make sure that it doesn't affect the results substantially. Now, let me remind you, on Tuesday, I did two problems for you, and I showed you that the transient amplitude, that term that dies out, has a big amplitude for the first few fraction of a second, and then eventually it stabilizes and reduced to the transient to the steady state response. So that's why you have to be careful. You design it for steady state, but you may have to go and check to see if that transient caused, you know, big amplitude initially, which can actually damage the equipment or cause destruction of the properties. Okay. All right. Let's move on. The magnitude x and the phase theta of the steady state response as a function of frequency is a function of driving frequency. We know that already. That's what this thing says. Now, we already know all these. This was all the review so far. So I talked about almost, I think I've been talking about 20 minutes, 25 minutes, and it was all review. This you already have seen. Now, it is convenient to have these things in a different form. For example, notice that if you look at this expression, I can take omega n squared out as a factor. I can take it out. So I'm going to have 1 minus omega squared over omega n squared. If I take omega n squared out of this, I'm going to take it out of that also, and you're going to have 2 zeta omega over omega n quantity squared. You require some algebra. You do some algebra. There's no doubt about it. And you write things in terms of omega over omega n. Please go ahead, factor out omega n squared out of this expression, and you see that this denominator actually becomes parentheses 1 minus r squared, where r is this frequency ratio. So 1 minus r squared quantity squared plus 2 zeta r squared. You have to do the algebra to believe me. Otherwise, you just have to trust. So you divide through by omega n, factor out omega n, and clean up. And remember, we're going to define something as the ratio of the two frequencies, which is called R. R stands for ratio of the driving frequency over the natural frequency. And look, that X that you saw here, and if you non-dimensionalize it, okay, non-dimensionalize it. So I'm not writing X equal to, I'm writing xk over f naught, non-dimensionalizing, because notice that x has a unit of displacement. It's the amplitude of displacement. And if you look at f naught divided by k, f naught divided by k also has a unit of displacement. So this thing is non-dimensionalized. No dimension here, okay? Because it's displacement over displacement. And if you clean it up, it's going to look like that. 1 over 1 minus r squared quantity squared plus 2 zeta r squared. And the angle, the phase angle is also going to look like that. 2 zeta r over 1 minus r squared. This stuff is going to be with us for the next 3 weeks, 4 weeks. And it's very important. Okay, instead of the previous version where you had to write omega n squared minus omega squared, stuff like that, this is a lot easier, cleaner than having in here omega n squared minus omega squared, etc., etc. So this is the cleaned up version, the compact version of what we had before. So if you gave me R and you gave me zeta, if you gave me R and you gave me zeta, we'll do examples, you can find big X. Actually, you cannot find big X. You can find xk over f naught. But you know what your f naught is, you know what your k is, so essentially you know your x. Okay? Now, I can plot that. See this thing? This normalized amplitude, non-dimensionalized amplitude, that's why it's called normalized. You can plot it as a function of R. But look, the horizontal axis is the frequency ratio, R. The vertical axis is that entire expression, this expression, and the angle theta. So the horizontal axis is the frequency ratio, R, and the vertical axis is the angle phase in radians. Let's not worry about the phase right now. Let's concentrate on this one on the left, and we're going to see a lot. A couple of things that you can observe here. Actually, I'm going to go on the next slide, which is, these are repeated. So let's go there in a minute. This is so important. This thing is so important that most people give a name to it. It's called dynamic magnification factor. Okay, because notice that F naught over K is a static deflection. If you have a spring, you apply F naught to it, it's going to stretch, it's going to deflect. So X over static deflection is the same as xk over f naught, and this has no dimension, and this is called dynamic magnification factor because it's this thing that will be bigger than 1, and it's going to make x larger than the static value. Okay. Now notice that there are different, these things depend on, because depending on what psi is, you can have a different curve. A couple of things you notice: when psi goes to 0, when psi gets smaller and smaller in the limit when psi is 0, it's undamped vibration. Notice that when R is 1, you have a problem. The denominator is 0. In the limit, when psi is 0, when there is no damping, R equal to 1 is trouble, because R equal to 1 is omega equal to omega n, and the amplitude goes to infinity. See that? For undamped response at R equal to 1, where omega equal to omega n, we had resonance. That means this goes all the way to infinity at R equal to 1. What stops it from going to infinity is that tiny little damping. As long as you have damping, this will never go to infinity. Okay? It has a maximum value, it will have a maximum value, but it will never go to infinity. That's the key. And the same thing, by the way, with the phase. If there is no damping, actually, when there is no damping, you look at the phase, it's 0, sudden jump, all the way to going through pi over 2, all the way to pi after that. Okay? So no damping, it's a flat line here. Sudden jump, going through pi over 2, through resonance, and then flat pi angle. But if there is a damping, then that is not it is not a sharp jump, step jump, but it is actually smooth. However, the same behavior is showing up. Now, this is repeated for your own convenience. It's the same thing that is from the previous diagram. Note that as the driving frequency approaches the undamped natural frequency, as R goes to 1, as R goes to 1, this magnitude, see that as R goes to 1, the magnitude of the amplitude increases, increases, increases. It reaches a peak and then drops, 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 if R is bigger than 1. Now, if it's undamped, it goes all the way to infinity, but damping will make it reach a peak and then drop. Now, by the way, you also notice that uh, you notice that uh, notice that the driving frequency, when the driving frequency approaches the natural frequency, the phase shift crosses the 90-degree 90 degree phase difference. You can see that. You see, as the driving frequency approaches the undamped natural frequency, okay, there is a jump here of through 90 degrees all the way up to pi. That's what this is saying. We'll do some examples. It becomes more clear. Now, when 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 omega is very small compared to omega n, that means r is very small. See that? When omega is very small, r is very small, because r is actually omega over omega n. Small omega, small r. So as we go to the left, actually, the amplitude decreases and it reaches the static uh, uh, static deflection. Because notice that as r goes to 0, we are reaching 1 for the amplitude. In other words, this x, this whole thing, xk over f naught becomes 1. And if xk over f naught becomes 1, x becomes f naught over k, which is static deflection. So as we go further to the left, you're approaching the static condition. And when r is very, very big, when omega is very, very big, r is bigger than 1, and it's bigger and getting bigger and bigger, actually the amplitude decreases. The amplitude x decreases because these are constants, right? These are constant. You can see that the amplitude x decreases because this whole thing decreases. This axis is this whole thing. This is decreasing, so x is decreasing. And the reason this happened, when the driving frequency is very, very big, then actually the mass will not even move. Okay? That if that force is applied to the mass at a very, very high frequency, the mass does not even have the time to move. That's why the deflection doesn't deflect much, doesn't displace much, and that's why this is going to 0. And this is what it's saying. So as omega becomes very large, the amplitude right there approaches 0 because the mass will not have the time to move. Okay, let's move on. Another thing that we observe here is that, well, at r equal to 1, no damping shoots to infinity, but damping will stop it from going to infinity. That much we know. But the peak of the amplitude is not quite at r equal to 1. It is not very far from it either, but it's not quite r equal to 1. R equal to 1 in the undamped case actually shoots it all the way to infinity. When there is damping, yeah, it doesn't shoot it to infinity, but a little bit to the left of it, the amplitude is even higher. However, because these are close to the resonance, people usually don't worry about the fact that these peaks are a little bit to the left of r equal to 1, particularly for light damping, okay? Light damping like 0.01, 0.1, 0.25. You can see that there's not much difference between this point's R, and this point's R, okay? So, but using standard calculus, we can find out exactly what these locations are. So, because you can find the derivative of x, derivative of this whole thing, not necessarily big X, with respect to r, set it equal to 0 and so on. If you do that, the peak value for whatever zeta you're talking about, the peak value is actually at these r locations. And the actual height of the peak value is something like that. Okay, so as I said, notice that uh, for uh, these R locations are not very far from R equal to 1. Okay, when you are, when you are close uh, to resonance, you can see that there's not resonance means R equal to 1, okay? The peak value location is relatively close to it. Now, by the way, if zeta is less than 0.707, uh, sorry, bigger than 0.707, there is actually no peak. You can see that. There is a peak only if zeta is less than 0.707. Okay? All right. Now, this is the same thing that I showed you twice already. Okay, but there's a statement here that when you calculate the phase angle, make sure it's between 0 and pi. Okay, make sure that the phase angle is between 0 and pi, because when you use a calculator to find tan inverse, it doesn't always give you angle between 0 and pi. It may give you something between pi over 2 and minus pi over 2. If you ever get go to that go to that range, minus pi over 2 and pi over 2, then you have to adjust it so that you basically add a pi to it so that it puts you between 0 and pi. If you get a negative number, for example, for theta, then add pi to it and it puts you in the range 0 and pi. Because the calculators are programmed so that the angle they spit out for tan inverse is between plus pi over 2 and minus pi over 2. But this whole thing, in this whole subject of vibration, you want the phase angle between 0 and pi. So if you ever go into the negative range, just add a pi to it. Okay, you'll see in an example. Let's look at this problem. We have the mass and the stiffness of the spring and the damper and the driving frequency 132. This omega is 132. And we are told that F naught, little F naught is 10. By the way, little F naught being 10 means that the big F naught is just 10 times your M. No big deal. Okay, but in this problem, they're giving you little F naught. I don't know why they, this is out of Inman. I don't know why he does it like that. But anyway, doesn't matter. He could have given us big F naught. No problem. It says find the steady state response. In other words, all that ugly stuff for the transient, which gave us this horrible expression, just forget about it. Okay, just do the steady state response. Okay, good. First thing that you need to remember. So what you need is big X and theta, because the solution for the steady state is big X cosine of omega t minus theta. Okay. So first thing that we need to do, we have to find omega n, because remember, big X, and I don't want to use that ugly expression that big X is equal to F naught divided by square root of omega n squared minus. I don't want to use that. I want to use the R business. Okay, so I need omega n, and as soon as you get omega n, you need the damping, the critical damping, by the way, it's right there. But first of all, if you find the critical damping, you're given the C, find the damping ratio, and this is an underdamped situation. This is an underdamped situation because it's less than 1. Now, you can use this, but I don't want to do that. I want to use the form that I like, big X equal to this. But notice that I had the expression for big X times K divided by F naught was equal to 1 over that. But if I want big X, I take my K on this side, I take my F naught on this side, there it is. Isn't this a lot nicer, more user-friendly than this? They're saying exactly the same thing. It's just that it looks easier to work with, okay? So you can use this expression, and it looks like here I used it, but you could have also found R and plugged it in that expression. Either way, you can use this, but that defeats the purpose of writing things in terms of R, but that's okay. You can use this. Omega n was 132. Omega was 132, so we are dealing with resonance. You can see that these two are the same. Omega n and omega are the same. So this thing is 0. These are the same. And you get 0.034. Now, if instead of omega being 132, I use 125, so if it's not the resonance condition, this was omega n, this is omega. And in the first case, I assume that these are the same. at resonance. But if I look at a slightly different value of omega, 125 as opposed to 132, we are no longer in the resonant condition, and you're going to get big X. If you just plug that in, 0.005, about 10 times smaller than that, 10 times smaller than that. So resonance, close to resonance, this is not even the peak. This is not even that maximum value. At r equal to 1, the big X is going to be large. Doesn't go to infinity, but it's large compared to around it, which is not at resonance, but 10 times smaller. So a slight change from 132 radians of the driving frequency to 125 radians per second driving frequency, about 5%, will give you 10 times smaller amplitude. Okay, that's one example. So we have a piston here, 100 pounds. This is not the mass, this is the weight, okay? Is supported by a spring here and by a damper, dashpot. The value of C is given, K is given, and obviously they're parallel to it, okay? And we are to find the steady state displacement as a function of time and the maximum force transmitted to the base. Okay. Now, a couple of things I want to say about, a few things I want to say about this. Okay. First of all, what the heck? I mean, this pressure is right here. The pressure applied to the top of the piston is right there, by the way. And the area of the piston is 80-inch squared. It's a fluctuating pressure. So you can see, although this is not quite realistic, but in the case of an internal combustion engine, you have a pressure here, which it's not quite like that. I understand that, because as soon as there is explosion of the gases, ignition of the gases, there's a big value, and then the air is or the gases are pumped out. So basically, it doesn't look like that. However, what is this K? Where does that K? This is probably your connecting rod. Okay, your connecting rod provides some kind of a stiffness, some kind of a resistance to the motion of the piston. So I'm just giving you an example. We draw a K here, but we don't actually literally have a spring in there. The other thing is that this damper, we don't have a damper there. What we do have, probably because of the friction on the side, you find an equivalent viscous damper, and that's what you're going to do in 2 weeks, and you assume that actually there's a damper there. This damper is really not there. It's the friction with the walls that is allowing us to replace that friction with some kind of a hypothetical, man-made damper, a human-made damper. Okay. All right. But anyway, we want to find a steady state response, and also at the end, how much force is transmitted to the base. Base meaning your engine, basically, the rest of your engine. Now I need the mass first, so I take W and divide it by G in 32.2 feet per second. Feet per second squared. I'm sorry, wait a minute. 100 pounds divided by G, 32.2 feet per second squared. And the thing that you're going to get is roughly 3, and this is a mistake. This is not sling, this is called slug. Pound over G in 32.2 is not sling, is a slug. So this is wrong. Okay. Yeah, I'm fixing it right here. So omega n is root of k over m. K is this. And notice that for m, I didn't use this value. I used, in my calculation, I used a 12 here. So this 12, where did it come from? This was feet Let me see now what I'm doing. Everything I'm writing everything in terms of feet. Okay. This lynch is definitely wrong. We know that this is slug. So what I'm doing here is this 200 pound per inch. I'm multiplying it by 12 to get a pound per foot. Okay, so I'm converting K to from pound per inch to pound per foot. There are 12 inches in 1 foot, and therefore, if I multiply this thing by 12, this is going to be a pound per foot. And this is, of course, this was wrong. This is a slug, consistent unit, and you get 27.8 radians per second. Okay, good. That's wrong. Okay. Slugs. Now, the damping ratio is C that's given to you, which is right here, 85, divided C critical. C critical, you either write it like that, or you write it like this, either way, and you plug it in. I mean, if you found omega, if you want, you can use this omega, and you can use your, which is 27.8, and you can use the mass in slugs right there, and you get this. So this damping ratio, remember, has no units. 0.492. This is a big damping value ratio. But anyway, that's what it is. Okay. This is an underdamped situation because that thing is less than 1, which means that you can use the stuff that you learned. Because these things that we did today, they all assume that we are dealing with an underdamped situation because we had a sine and a cosine and all these things. Good. Now let's find the frequency ratio. Omega was given to you right here, 30. Omega is 30, right there, 30 radians per second. Omega n, we just calculated, so the frequency ratio is 1.079. Actually close to resonance. You can see that. See close to resonance, but that's fine. Let's move on. Now we plug it in this expression. Remember, this is nice and clean because I don't have omega n squared minus omega squared anymore. I already did the cleanup. So what do we know? We know the value of R, we calculated. We have F naught. Let's go back here. F naught is this number right there. Actually, this is pressure. You have to multiply it by 80 to get the value of F naught in pounds, okay? So you take 0.625, multiply it by 80, and that is going to be your F naught. Yep, 0.625 multiplied by 80. The K, we already did it. 200, it was pound per inch. So multiplied by 12, pound per foot. So this is all consistent. And the value of R, we just calculated right there, plug it in, and you get 0.01938 feet. Okay? This is the amplitude, and you can find your phase. Just plug in the value, phase angle, plug in the appropriate value. You have psi, you have R, you have tan inverse, and you get a negative number. We do not want to get a negative number for theta. Theta is must be between 0 and pi. So what we do is we add pi to this. Yeah, we add pi to it. This is the correct phase angle. I want you to sit and think about why do we want theta to be between 0 and pi? Think about phase difference. Does it make sense? Is it not better to say that the angle is always between 0 and pi? Yep. So anyway, think about it. Now, there is a steady state solution. Amplitude, big X, phase angle right there. Okay, 1.724 right here. It's minus. It's minus theta, so that's why you have 1 minus or omega 30t minus that, because remember this is the theta is this, and then the expression inside is omega t minus theta, so this is theta. Now, when it comes to finding the transmitted force to the base, now what actually is transmitted to the base is the force of the spring and the force of the damper. Force of the spring is just k times displacement of the spring. Force of the damper is c times the velocity of the damper. And you have this expression right there. You have this expression. Just plug it in. Just plug it in. K times big X times cosine minus C omega, the derivative of this thing, is minus C omega X sine, right there. Now, of course, yes, I know that I know omega, I know X, I know theta, but I wrote it for you in general, that expression. If this is my solution, big X cosine omega t minus theta, it's going to look like that. And of course, I have values for all of these, but notice that the maximum value of this expression, the amplitude of this expression, because these are the same angle, the maximum of this is kx squared plus this squared. Remember, this is the trick. So if you plotted this, the amplitude of it is going to be square root of kx squared plus c omega x squared. So this is the maximum amplitude. I know x, I know k, I know c, and I know omega. Just plug it in. So the maximum force transmitted to that base, to the engine, is 67.9 pounds. Now, let me show you a different way of doing this thing. Just be patient. This is fine. This is all done. But I want to show you a different way of doing it. This is the mother of all equation for the system that we have. An XP, we just said that it is this. Last hour or so, we have been haggling with each other on that issue. Now, this thing is the transmitted force. It's right there. See that? It's right there. Transmitted force is Cx dot plus Kx. Fine. So can I not say this is equal to F naught cos omega t minus mx double dot? Sure, I can do that. This is what I want is equal to F naught cos omega t minus mx double dot. Okay, and I know what x is. It's right here. This is what x is. So you just plug it in. Just plug it in. Literally plug it in. And right there. So see, this is there. Double dot, double derivative of that is right here. Just do a little bit of a cleanup here. This stays. This minus. Uh, Actually, this is there should be a little minus inside of that too. This is an error. Hang in there. Yeah. X double dot, when you differentiate it, you get minus mx omega squared. Okay. There's a minus here that I missed. And that minus makes it a plus right there. So can I not say that the maximum of this, can I not do the same trick here? You say that it's square of that plus the square of that. Can I not say that? Oh, I did it, right? The maximum of this is the square of kx and the square of c omega x right there. But can I not say that same thing here? Square of that plus square of that. The answer is no, because this is omega t, this is omega t minus theta. Here, it was both of these were omega t minus theta. No problem. As long as these two are the same, you can say square of this plus square of that, square root. But if these are different, this one is omega t, this is omega t minus theta, you can't do that because these are out of phase of each other. If you plotted this, you didn't do that. Don't do this. You can't do it. But if you plotted this and you look at the maximum amplitude, that's okay. You're going to get 67.9, but you cannot just go ahead and take the square root of this squared plus that squared. You cannot do that because of what I just said. Let's look at another example. Let's see how much time. I think we've gone less than an hour so far. Yep. Let's move on. So we have a setup like this, uh, pivoted here, damper there, spring here, spring there, and of course we're subjecting this thing to a sinusoidal harmonic loading. But the loading is not F force, it is moment. So what this tells you is that the easiest way to do this problem is turn into everything in terms of change of angle of that bar, which is theta, right? Everything in terms of theta. Okay, you already know, you look at this thing, you realize that this rigid bar is going to tilt by angle theta, and lo and behold, the exam showed you, the test one showed you that it's better to write everything in terms of theta. Don't try to bring x into this picture. And I'm going to show you in a minute that the mother of all equation for this, sum of all the moment about the pivot point A equal to uh, uh, the applied force, okay? Sum of, you go through that route, sum of all the moment equal to mass times acceleration, and then you're going to get this equation. We'll do that in a second. So here's the bar, free body diagram of the bar. If the bar tilts by the amount theta, the damper says, no, 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 you can't go down, because remember, the damper was up here. You can't go down. That's what the damper says. And the spring, this is spring want to stretch, this this spring I want to compress. The spring says, no, 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 you can't come up. This spring, on the other hand, this spring wants to elongate. They both want to stretch actually, and they both say, no, 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 you can't come down. This says, no, 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 can't go up. No, 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 can't go down. And of course, damper reacts like that. And here we have a moment. Reaction force at the pivot is not important because we're going to take the moment about this. Patiently take all the moments about that point A, and we're going to say the mass moment of inertia of the bar, whatever it is J about A, okay? And just write it down patiently using this convention as positive. Any moment that goes this way, positive. Any moments that goes the other way, negative. Okay. For example, notice that this is positive because it goes in that direction, but this gives you a moment opposite to that. The damper gives opposite, negative. This spring and that spring, they both give negative moment. Okay. And just take everything to one side. J about A is J about the center of mass plus parallel axis theorem, basically ml over 4 squared. This is the parallel axis theorem. Okay, so because we know the bar, the the bar of mass m, length L, about the mass center is J is ml squared over 12, but then you also have to add, using parallel axis theorem, the mass of the bar times the distance from the center of mass to the pivot point. End result, there we are. That's what we've got. Okay, this is the equation of motion. Okay, please make sure you can do this thing because this kind of a thing was given to you on the test. All right. But except that the only thing is that we didn't have a harmonic loading here. It was a free vibration. I just moved this thing, let it vibrate up and down. Okay. Now, so all the formulas that we did are still valid, except that instead of force, if not, I have a moment amplitude, and whatever the effective stiffness is, effective constant. Please do not put a K here because you may get the impression that this K is the stiffness of that spring on the left or the spring on the right. Okay. No, this is the effective spring, which means for us, let me go back. This is the effective spring. This whole thing is effective K. This whole thing. I just plug it in. Now we're going to need the value of R, by the way, so let's find out. First of all, here is this whole thing that I mentioned. Plug in the values that you know, you get this. Effective mass. Let me go back to the previous slide, and I'm sorry for going back and forth between these things. This is the effective mass. This is the effective mass, the whole thing, 7mL squared over 48. There we are. So natural frequency is right there. Just plug these things in, and you're going to get 63.8 rad per second. The m is mass of the bar, which was actually given to you in the statement of the problem. Okay. K was given to you, and m was given to you. Okay. Little m was given to you, mass of the bar. And we are told that the frequency of a forced vibration is 400 RPM. And remember, the load was m naught cos omega t. Okay, you're told that uh, that omega of that harmonic load is 400 RPM, which is 41.88 radians per second. The frequency ratio is the ratio of omega over omega n. You just plug it in. So this number over that number is 0.65, because I can go in here, plug in the value of R, K effective we calculated, M naught was given to us in the problem, and yeah, I need a psi here. Zeta, I need zeta here. I need the zeta. Effective damping coefficient is CL squared over 16. Let me go back, and I'm sorry again. Let me go back. This is the effective, this is the effective damping coefficient. Okay, so right there. Okay, and just find the value of zeta, C effective over critical. C effective is this number, that whole thing. Okay, and critical is 2 square root K effective, M effective, and we have K effective and M effective. Just work it out. Okay, this problem, the statement of the problem says, what should M naught be so that you get the biggest angle is 15 degrees. So if you go back to the statement of the problem, and we have the time, we can go back, read what it says. It says, find the maximum M naught such that the steady state amplitude of angular oscillation is 15 degrees. So you have the amplitude of the oscillation, big M, you have the big M is, uh, uh, sorry, not the amplitude oscillation. You have the, you want to find the maximum M such that the biggest theta is 15 degrees. Okay, so let's go back. Maybe there. Right. So the theta, amplitude of theta, biggest theta is the amplitude of theta, 15 degrees in terms of radian. Just plug it in and get your M naught. Biggest theta is the biggest angle theta is that amplitude, big theta. So anyway, you just go here, put this thing 15, everything else you know, you calculate your M naught. There we are. Two more problems. So it says we have a 10 kilogram mass here, and it has a motor in it. It's something inside of it is turning, so that actually make it vibrate back and forth harmonically. Okay, so go back and forth harmonically. Uh, an unbalanced motor whose speed n in revolution per minute can be varied. The oscillator is restrained by horizontal motion by a spring. I have the stiffness of that spring right there, and by a damper. I don't know what the value of the damper is, but it says that damper is resisted by a force of 30 Newton at that speed. So immediately it says that damping force at that velocity is 0.5, which means that immediately I can solve for C. But anyway, let's move on to the question that it was. It determined the viscous damping ratio, determine the viscous damping ratio, and plot the magnification factor big M. Okay, remember that big M was that 1 over square root of 1 minus r squared dot dot dot. I said that some people call that big M magnification factor. Okay, it says plot that. First find zeta and then plot big M and answer something. Determine the value of M for the corresponding motor speed. Okay, first thing, we know the mass of the block. We know the stiffness of the spring. We are told that the force of the damper, Cx dot, is 30 Newton when x dot is 0.5 meter per second. Right there. This line says exactly that. The force of the damper is 30 Newton when the speed is 0.5. So immediately we can get the C out of this. And of course, you have these two, you get the natural frequency. If you have the C, okay, if you have the C, you always know C critical is 2m omega n or square root 2 square root of k times m. Either way, okay? So because I calculate omega n, I'll just use this form of it, and zeta is going to be 0.289. So zeta, we just got. Now it says for that value of zeta, plot m. Now remember, m was this. This is the dynamic magnification factor. This is M is this dynamic magnification factor. And notice in it I need R. Okay, I need R and zeta. But it says plotted as a function of R. So I'm not, R is going to be varying. You can see that. R is going to be varying. And if you plot it, you can see you get this amplitude variation. R equal to 1 is a little bit to the right of that peak. We already know that. Peak is a little bit to the left. And in fact, what I have done here, I have zoomed into the area from 0 to 2 so that I have a better idea of what's going on here, because the question said, statement of the problem says, give me the maximum M. The magnification factor, the biggest dynamic magnification factor, what is it? 1.89. Okay, because it's this thing that's going to be multiplied by uh, uh, you know, static deflection or static angle uh, to get the actual deflection, maximum deflection. So, and this happened at this peak. This peak, just look at that. It happens at around 0.913, not at R equal to 1. But because these are so close to each other, it's easier to put R equal to 1 in some calculations and get the maximum value of R. So what you get if you put R equal to 1 is not really maximum. It's a little bit less than maximum. You can see that right there. R equal to 1 gives you that height, where at the actual peak is right, right up there, 1.89. If you calculated this thing for R equal to 1, obviously this goes away, right? This goes away. When R is equal to 1, this goes away. And you have 2 zeta here squared, so you get 1.73. Not very far from it. It's a little bit smaller. So it says, plot the response of this 50-pound body. The spring is given here. The dashboard is given here under this harmonic loading. This is harmonic loading, okay? Over the first 2 seconds, assuming that the initial conditions are x equal to 0 and v equal to 6 feet per second. Now notice, first of all, if I wanted to do the steady state response, I don't need these initial conditions. But it says, no, 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 I want you to get the total response. In other words, not only the steady state response, you have to do that for sure, stuff that we did in the last half an hour, 45 minutes, but also make sure that you impose these initial conditions to get the total response. In other words, the total response being the dying out solution, the transient one, plus the steady state. Okay, so let's go ahead and do that. First of all, the weight of this object is 50. To get the mass, we divide it by g, and you get 32.2. And of course, this is slug. I made the mistake in the one of these other problems. I wrote a slinch here. No, if you do 30.2 pound over 30.2, 32.2, you're going to get something called slug. The mass is this. Now that we have the mass, we have the stiffness. But remember, this stiffness is given to you in pound per inch. Everything is going to be in terms of feet, okay? So I have to multiply this thing by 12 to get basically 1,200 pounds per foot. Okay, that's the stiffness. Divided by that many slugs, you're going to get the radians per second. Now, the damping ratio is the C that's given to us right here, 18, right there, divided by C critical, and C critical, one way to do it is 2m omega n. We have m, we have omega n, you multiply it out, you're going to get this number. It is an underdamped situation, so everything that we have done in this lecture applies. Okay. Now, the frequency ratio, omega, that's given to us, it's 60, omega is 60 right there. Omega n, we just calculated, you get 2.158. Okay, good. If I have omega, if I have r, sorry, and I have zeta, you can find the magnification factor. There's the magnification factor, 1 minus r squared quantity squared plus 2 zeta, zeta is right here, times r squared. You just plug it in, you're going to get this. This is magnification factor. Now, what is the maximum amplitude, the amplitude of the solution? Remember, the amplitude of solution is the normalized one was x times k over f naught equal to m. If you rewrite that, it's going to be big X. That's what you want. This is the amplitude of the oscillation, force oscillation is equal to m f naught over k. Because remember, big M was x times k over f naught. So another way of writing it like that. And I got the m right here, 0.265. I got the F naught right there, 160, see that? F naught is 160, the amplitude of the force, and divided by K, K is right there, but multiplied by 12 because everything has to be consistent in feet, and you're going to get the amplitude of oscillation is 0.0354. So if the force is applied like that, this will oscillate, and in the long run, in the steady state, it will go by an amplitude of 0.354. Initially, because of that transient response that we're going to calculate a while, this amplitude is not going to be that. It's going to be some, you'll see that actually, there's going to be possibly some values higher, and then eventually it stabilizes, and this is going to be the steady state amplitude. We'll get there. Now, damping frequency, we need it because we're going to find the transient portion of the response. Now remember, the total solution is a transient one. This is the one that's dying down, and this is the steady state. And this you can do it two ways. This transient one, you can write it like that, amplitude and phase. This stuff we already calculated. I haven't done the theta yet. I will do that. Okay. I found the big X in the previous slide. I found big X. I haven't found theta, and I need theta. Okay. But the point is here is that you can write it like that. The transient one, you can write it like this. You need to find A and phi. Good. Or you can write it as a constant e to the, e to the this exponent times cosine plus another constant. In one of the earlier exercises, or not exercise, one of the examples, I could have called this thing A1 and A2, or constant, C1 and C2, A1 and A2. It really doesn't matter, okay? So you can do it like this, or you can do it like that, whichever is convenient for you, okay? Uh, and there's a mistake here. This is a mistake. This is a mistake. This should not be omega n. This should be omega and omega. Of course, when I do my calculation, I will fix it. Okay. This is not omega n. This is the frequency, the driving frequency. This should be, I think it was 30, right? This should be 30. 30, not omega n. Move on. So I already know x. I will use this approach. Let's find the theta first. Theta is, we have a formula for it. Plug it in, you get 2.9. And I'm really sorry about this omega n. In the lecture, I fixed it, but because this is pre-recorded before, this recording is done before the lecture, I ran into this issue. I'm going to fix that in a minute. Okay. Now that we have, now that we have theta and x, it's just a matter of plugging in that horrible expression for phi and a, because you know x naught, you know v naught. Where's the v naught? Oh, right here. You know v naught. These we already used and calculated, no problem. You plug it v naught, whatever it was it from rest? I can't remember. X naught was given as 6. I can't remember. Let's go back here. Let me go back and find out what it is. I'm sorry. It says x is 0, x naught is 0, and v naught is 6. Okay, so yes, yes, yes. Go here, plug it in, and you're going to get your a and phi. A and phi. And you know everything. You know a, you know phi. I fixed that mistake here. Remember that mistake? I said this should be omega, not omega n. That's fixed here. That's very good. So you just plug it in. Uh, bad boy. This should be 30. Bad boy. This should be 30. This omega. This thing is, it should be 30 because what I wrote here is omega and bad mistake. Let's see if I can fix this thing. This should be 30 because I believe the driving frequency was actually 30. Let's go check it. Let's go check it. 60, not 30. 60, right there. 60. 60, not 30. 60. Let's go fix it. Uh, yeah, this should be 60. This is 0.034, which was big X, and this is 2.9 that we just did it in the previous page. 2.9. Okay, very good. And these are the damped frequency, 27.2. We did it right here. 27.2. This is the damped one. Omega D equal to 27.2. Very good. And this is A, 0.212. It's right there. And phi is 1.408. It's right here, right there. So go to the next page. Actually, okay, we already did this. I wrote it here for your convenience. And once again, this is a mistake. This should be 60. This should be 60. Good. Let's go back. 60 is fixed. Everything is good. This is your A. This is your xi omega n. This is your damped frequency. Here is your phi. Here is your big X. Ah! This should be omega, not omega n. Right. Driven frequency. Let's fix this thing. Where is omega? Right there. Excellent. And finally, this is your theta. This is your theta. That is your theta. This is your omega. And everything is good. All right. And you plot it. You can see that. You can plot it. In the steady state, this whole thing will die down. And you're basically dealing with this. That's why the amplitude is constant, 0.0354, and the frequency is 60. Initially, this is causing a problem. You can see that you have a large amplitude because at initial condition, etc. But it dies down. Okay, and yep, that's wrap it up. So I'm really sorry for some of these mistakes, but I fixed it as I went along. Okay, and good luck. See you in the lab later today.